Welcome back. In this part of this lecture, we're going to examine what we can do with carbon dioxide. We saw in the last part that emissions of CO2 have contributed to an unprecedented rise of the concentration of carbon dioxide in the atmosphere. It is greater now than it has been for any time going back over several million years. If we have the technology in place to capture carbon dioxide, and that technology, as we've seen, in some cases is established, what do we do with it? Is carbon dioxide simply a waste product? Is it something that we have to pay to get rid of after we've already had to pay to capture it? However, can carbon dioxide be used as a raw material? What happens if we have renewable power feeding all the power grids? What happens if we use that power to get hydrogen by electrolysis? Can we make the combination of carbon dioxide and hydrogen economically viable to displace crude oil as the go-to raw material? If there's economic incentive, then usually, as we see from history, there's an incentive for manufacturers to go and use it without any legislation being required. Commercial incentive, sadly, is stronger than any other when it comes to changing the way that the world works. So what I would like to do is to paint a scenario. I'm going to make some assumptions to start with and to see where these assumptions might lead us. So let's assume that direct air capture, bioenergy with carbon capture and storage, and other carbon dioxide capture schemes are ubiquitous and widespread around the world. In other words, there's a lot of waste CO2 in pure form available. Let's also assume that zero or negative carbon energy dominates power grids. Let's furthermore assume that because of the widespread nature of carbon capture, the purchase price per tonne of carbon dioxide is roughly $10 per tonne. Which begs the question, what do we do with greater than 10 to the 12 tonnes of carbon dioxide? Well, we could treat it as a waste product. There are numerous ways in which we can dispose of carbon dioxide. One method is to pump it underground, maybe into old oil wells, and to hope it stays there. Another method is to turn it into stone. Both of these methods have been demonstrated in pilot projects, and both of these methods could be used to either bury or mineralise carbon dioxide. Either way, it takes it out of the atmosphere, which is good. One key drawback, however, is that these are waste disposal processes. Waste disposal processes require paying for. You're paying for carbon dioxide to be captured out of a process, and then you're paying again for it to be disposed of in a suitable manner. How about we change things around? Can we incentivise people to capture carbon dioxide anyway because it's a profitable thing to do? Why can't we use carbon dioxide as a raw material, displacing fossil raw materials? This isn't so impossible. It might sound impossible, but there's one key chemical reaction that has been routinely used in the chemical and process industries for over 300 years. Carbon monoxide plus steam gives an equilibrium with carbon dioxide and hydrogen. So, why don't we run this equilibrium backwards? Why don't we introduce carbon dioxide and hydrogen together with the right catalyst under the right conditions to give carbon monoxide and water? If we can find a green hydrogen source, then this could be a way to turn carbon dioxide into a mixture of carbon dioxide, carbon monoxide, steam and hydrogen, which with a little bit of careful treatment, removal of water, removal of carbon dioxide, gives you synthesis gas. And we've already seen that synthesis gas is a very potent raw materials for existing parts of the chemical industry. So, if we think of the chemical conditions required, the old process conditions, or the old process conditions from my standpoint, are typically iron catalysts, temperatures ranging between 250 and 350 degrees Celsius, pressures ranging between 10 and 50 bar. So carbon monoxide shift typically is energy intensive. However, innovations in catalysis could mean that that all changes. Already in your era, there have been some innovations in the laboratory that suggest bimetallic palladium electrocatalysts can undertake carbon monoxide shift at temperatures as low as 80 degrees C. and pressures far closer to atmospheric. So could future catalysis with a green hydrogen source and captured CO2 be a key route for synthesis gas production? Let's see what we can do with synthesis gas. I know you already know part of this story because the Ghost of Chemical Engineering Past talked about the Billingham site, which was founded in 1918, a very long time ago, that all relied on synthesis gas. However, there's other parts to this story, because there's a set of reactions known as Fischer-Tropsch reactions. These are catalysed reactions where you polymerise synthesis gas into hydrocarbon waxes. The hydrocarbons you get are typically between 32 carbons and 64 to 128 carbons, and they're linear, so these produce long-chain linear alkanes. Now, these long-chain linear alkanes can be made into more useful products by hydrocracking. It needs hydrogen, but then again, we've already had a source of hydrogen present for our synthesis gas production. So a combination of hydrocracking, isomerization to turn linear hydrocarbons into branched hydrocarbons, and linear hydrocarbons into cyclic hydrocarbons and sometimes aromatic hydrocarbons, gives us then a whole mix of different hydrocarbon families which we can distill out into their various fractions. And we can blend things such as naphtha, jet fuel, fuel gas, all starting from synthesis gas. This is established technology. It is low risk, and it has been used in parts of the world for 40 or 50 years. A lot of the fuels in South Africa have been made using exactly these processes for a very, very long time, with synthesis gas being derived from coal. So, breakthroughs in catalysis are going to be one of the things that allow us to think about carbon dioxide in a very different way, to stop treating it as a waste product and to start treating it as a potential raw material. If you look in the academic literature, a lot of research is being focused into this. How to make synthesis gas into aromatic hydrocarbons, how to make synthesis gas into ethylene, how to use CO2 directly to make polyols, of which ethylene glycol essential for the production of polyethylene terephthalate. We can also see carbon dioxide electrocatalysis directly into alcohols, methanol, ethanol, butanol. We can also see catalysis of carbon dioxide into solid carbon, ironically turning the waste gas from coal back into coal. So, can we reimagine chemicals production in the future? Can we centre chemicals production around carbon dioxide, hydrogen and renewable electricity? From these three things, we can use the hydrogen to make ammonia. We can use the carbon dioxide to make polyols such as ethylene glycol. We can use it to make graphite for the moderation of nuclear reactors. We can use it to make methanol, ethanol and butanol, all essential intermediates in the chemical processes. We can then make synthesis gas, and from that synthesis gas we have the ethylene value chain, we have the benzoene, toluene and xylene value chain, and of course we have the linear and branched hydrocarbon value chain via Fischer-Tropsch. So, could this be the block diagram of the chemical site of the future? It's not all that impossible, because here is a picture of a chemical site in Secunda in South Africa, which relies on synthesis gas to make jet fuel, diesel, kerosene and a whole host of commodity petrochemicals. Has the future arrived? In part, but there's still a long way to go because of course the synthesis gas here is coal derived, not carbon dioxide derived. But there may well be a future for carbon dioxide based chemical synthesis. This hopefully might allow life on Earth to continue as we know it. Back to our atmospheric concentration of carbon dioxide, there is the last 2,000 years worth of data culminating in your current day. Projections looking forward into the future, the area I am in, are many and varied. One projection says that net zero isn't attained. There isn't the political will to do it. There isn't the incentive to do it. Carbon dioxide concentrations keep increasing and increasing to 800, 900 parts per million. It basically spells the end of life on Earth as we currently know it. It doesn't have to be this way. With intelligent politics and good decision making, we can go forward and say, no, we can reimagine this. We can remove the carbon-intensive processes that are already in use today. We can decarbonise those essential bridging technologies that will take us forward to a point when we have consistent and reliable renewable power storage. And then we can decarbonise the atmosphere using direct air capture, using bioenergy with carbon capture and storage, and use that carbon dioxide in a way to power the global petrochemicals industry to make it far more sustainable, far greener, and far more adjoint with a green future. So, some key points. Can we use carbon dioxide as a future go-to raw material when combined with hydrogen and renewable electricity? Developments in catalysis are already happening in this area as a potential way to pave this breakthrough. Chemical engineers are going to be needed at all stages of this process, because without the chemical engineers, those catalysts will just remain a laboratory curiosity. With chemical engineers, they will become a major force for global change and global improvement. So chemical engineering, the chemical engineering of your era, is going to be a pivotal discipline to allow life on Earth, as we know it today, to continue.